Because so many ideas from probability stem from the set theory, we need to also recall our multiplication principle from set theory, that if you are making choices in a sequence, then you're doing that multiplication counting rule, where you multiply the number of choices for the first event times the number of choices for the second event, and so on and so forth. And usually you will see the word "and" as a key word for those. We want to choose this and this and this. And then we also have the OR probability formula that we talked about, which is the probability of the union of two events is calculated by adding the probability of the two events separately and then subtracting any overlap that might occur. Okay, so let's move on to our next example. A box contains 6 yellow and 4 red balls. 3 balls are selected from the box at random without replacement. Find the probability that. Okay, so really important pieces of information here is that there are 10 total balls in the box. We're going to select 3, and what's really important here is that we are not replacing them. Okay, so the first question says, what's the probability then that all 3 of the balls are yellow? So this one's fairly straightforward, like the ones we have been doing with the combinations. We want to specifically choose 3 yellows out of the total idea of just choosing any 3. So how can we choose 3 yellow? Well, there are 6 yellow total, and we have to choose 3 of those. So that would be a combination of 6, choose 3, because the order doesn't matter. We're just choosing. And then how can we choose any 3? Well, out of the 10 total, we would choose 3. So that would be our denominator. So again, I'm going to go to my calculator. I'm going to do a 6 combination 3 for the top, and I get 20. And then I'm going to go back in and edit that and take it out of 10 this time for the denominator. And I get 120. And then we can reduce that down to 1/6. So there's a 1/6 probability that you're going to choose out of those 10 balls, 3 that all happen to be yellow. Okay, what about the probability that you choose 2 yellow balls and 1 red? So this does have that "and" word, that keyword "and", that signals we're going to be doing a sequence, like we do 2 yellow and then 1 red. So this is a sequence of events. So it's going to set up similarly. We're still in general choosing for our denominator. Out of 10, we're choosing 3. So that's still my same denominator. But on the top, I'm going to have a multiplication. So I'm going to have, how could I choose 2 yellow? Well, that would be a combination of, out of those 6 yellow, we choose 2 this time. And, so multiply, and a combination that out of those 4 red, we happen to choose 1 of them. So I know my denominator is still over 120. That's the same calculation as before. And I'll just do this quickly for you, and you can follow along or pause in your calculator if you want to. 6 choose 2 is 15. And then we're going to multiply that by 4 choose 1 is 4. So we end up getting 60 out of 120, or a half on this one. So there's a 50% probability of that particular combination of things occurring. Okay, what about the next example? 2 cards are selected at random, without replacement again, from a well-shuffled standard 52 card deck. Find the probability that both are kings. So again, we are just choosing 2, so order is not important. That's how I can kind of get in the idea that these are combinations. We want to choose 2 kings out of all of these cards. So let's see, how can I choose 2 kings? That's a combination There are 4 total kings in the deck, and we want to choose 2 of those. So that's choosing 2 kings out of all the cards, out of a combination of 52, choose 2. Because this would be my choose any 2 cards. So if I do 4 choose 2, I get 6. And if I do 52 choose 2, I get 1,326. And then we can reduce that in our calculator. So some of this I'm letting you do in your calculator if you so choose. You can always pause me and do that. So if I want to divide that out, and then I'm going to hit math and enter, looks like that reduces to 1 over 221, or we could say it's approximately, if I move that decimal point over 2 places, it's approximately 0.45%. So it's pretty unlikely, less than 0.5%, that you are going to randomly draw 2 cards, both being kings. What's the probability that exactly one of your cards is a king? Okay, well, to do that, we would have to choose 1 king and then choose 1 not king, right? Anything else. So in order for that to happen, we're still in general choosing for our denominator. Out of 52, we're choosing 2. For the top, to choose 1 king, we would be doing a combination of out of those 4 kings in that deck, choosing 1. So a 4 choose 1. And, so multiply, we have to choose 1 not king. So out of the other 48 cards, we have to pick one of those as well. We know 4 choose 1 is 4, and 48 choose 1 is 48. With the combinations, anytime you're choosing 1, you just get that value back. And we already knew that the 52 choose 2 is 1,326 in the denominator. So if I multiply that out, 4 times 48 is 192 out of 6. This is a 6. And then I can divide that out. 192 divided by 1,326. I get my decimal answer, and then I'm going to do a conversion. Looks like that can be reduced to 32 out of 221, or it's approximately 14.5, I'm going to call it. So there's about a 14.5% chance that you at least choose 1 king and something else then. What's the probability that at least one of the cards is a king? So this is an interesting concept, at least one. So if you're choosing 2 cards and you want to know at least one of them being a king, that means one or both of them being a king. So one or both is, in this case, how you would get at least one. So really, what we need to do is just add our probabilities from A and B together, because this would be part A. How can we choose? Oh, sorry, actually, go back. That's part B. Choosing 1 is part B, and choosing both kings is part A. So we can choose 1 king or 2 kings. So this is an or. Is there any way to choose 1 king and 2 kings at the same time? No. So these are mutually exclusive, which means we should just be able to add their probabilities together. I'm going to go back up to their reduced fraction forms, since those are both out of the same denominators. That would be 1 out of 221 plus 32 out of 221, which would equal 33 out of 221. And if you divide that out, you'll get approximately 15%. So it just ups that percentage a tiny bit, right? If we add those two together, we get right at 15%.